So in this chapter, we want to really focus on making use of diagonal forces. I say diagonal because in year 12, a lot of the forces we worked with were either vertical or horizontal. We came across vectors which represent diagonal motion. There is some horizontal and vertical component to every diagonal vector, to every diagonal force. And we really need to be able to introduce and identify those components. As you can see, I'm taking effort to make a good representation of the diagram I'm going to be working with. Lots of labeling and annotation is still to come, so I recommend that you make a large diagram, or at least a medium diagram that we have space to add our components onto. I'm going to insist that you do a diagram for every question that we respond to. We will come up against exam questions that don't have any diagram, and we have to interpret fully the context that we're working with. So once again, a large scale diagram to show exactly what we're working with.
Before we get started, I do want to emphasize a key skill that we're going to need to be using while we're working with our vector forces. So once again, these forces are not just going to be horizontal or vertical, but they're going to be vectors. They're going to be diagonal, where they're going to have a horizontal component and a vertical component. And we need a way to easily evaluate those components. So here is an example. I've got an 18 Newton force and it's acting, or the direction it's moving, or the direction it's acting is 40 degrees above the horizontal. Now, this vector force has two components. It has a horizontal component and a vertical component, which I can show with these dashed lines. Now, these components are going to be used in lots of the calculations that we're going to be doing. So we do need to be able to find an expression, a workable expression that we can use with them quite easily. Let's start with this vertical component, which I've labeled A. Since I have a right angled triangle, I should be able to use SOHCAHTOA, right angled trigonometry, to find an expression. It's the opposite side, so I can use the sine function, and sine 40 should equal the opposite over the hypotenuse, so sine 40 is A over 18. We'll just rearrange that to make A the subject, and A is now 18 sine 40. Now we can work that out on our calculator, or we can actually just use that expression, which would keep an accurate value throughout our calculations. So 18 sine 40 is the vertical component. Horizontal component, I've labelled that B. This is the adjacent to the 40-degree angle. So we can write a similar trig expression. This time round, cosine 40 is going to equal B over 18. But similarly, we'll rearrange to make B the subject. B is 18 cosine 40. These two expressions can be used in our calculations. When we're resolving, when we're trying to find acceleration, when we're trying to find unknown mass, whatever it is, we can use 18 sine 40 and 18 cosine 40 within our calculations. Both of these have a similar form. 18 was the hypotenuse. Sine and cosine are trig functions that we chose depending on whether our component was the opposite or the adjacent in the right angled triangle, and then 40 was the angle size. So the syntax, the default setup is the hypotenuse, the trig function, the angle. All you need to do here is to choose the appropriate trig function. So for the opposite, we're going to be using sine, so 18 sine 40, and for the adjacent, we're using cosine, 18 cosine 40. So this should actually be quite quick for us to be able to determine an expression for these components. You don't have to write out the trig function expression every time. After the first couple of times, I do expect you to be quick fire and to be able to almost instantly tell me the components.
Okay, so here's an example where we have two forces and we want to try and find the resultant force. Not just the resultant, but its magnitude and direction. So we'll start with these two forces, P and Q. Angles are as given, 30 degrees and 45 degrees. Now, each of these forces can be broken into its components. It's horizontal and it's vertical. And let's actually get magnitudes for P and Q. 10 and 8, so we can get our expressions. Here, 10 sine 45. And the horizontal, I've got space, 10 cosine 45. Second force, break it into its components. We get 8 sine 30 and 8 cosine 30. Okay, now that that's fully labelled, let's actually try and find the resultant force. So the horizontal component is going to be made up with these two, 10 cosine 45, plus the 8 sine 30. They're both moving in the same direction, towards the right. And for the vertical, I've got two opposite directions. So I'm going to be subtracting the 8 sine 30 from 10 sine 45. Okay, just punching those values into the calculator, making sure we're in degree mode. And we get 14.0 and 3.071. So that's the resultant vector. We can sketch that and label it for its horizontal and vertical component. And yeah, this is a question that we're very used to. We should be able to find the magnitude and the angle for this vector. Its magnitude is going to be found using Pythagoras. And the angle, which I'll label theta, can be found using trigonometry. Okay, so inverse tan of the opposite over the adjacent. And that should lead to the angle of 12.372 degrees. And to be specific, we can say that that is above the horizontal or above the x-axis. So we know that it's not underneath or below that horizontal. Now, each of these forces can be modelled as a right-angled triangle. And if we're trying to find the horizontal and vertical components, that's the same as finding the adjacent and the opposite within a right-angled triangle. And we know we can use SOHCAHTOA right-angled trigonometry to do that. If we're looking for the opposite, we can use the sine function. The sine of the angle equals the opposite over the hypotenuse. And we can rearrange that to say the opposite should equal the hypotenuse multiplied by the sine of the angle. In this case, the horizontal is going to the right and the vertical is going up. The horizontal is the adjacent, so it should be the hypotenuse times cosine of the angle. The vertical is the opposite. It should be the hypotenuse times sine of the angle. And that's how we should be able to quickly generate expressions for these components. Once again, hypotenuse, sine of the angle, since we're working with the opposite, and hypotenuse, cosine of the angle, we're looking at the adjacent. On this third force, we have an unknown angle. That's fine, we can still label these. So for the opposite, it's P sine theta, also an unknown force, and P cosine theta. All right, we'll do some problem solving with these to find what these missing values are. Well, we've been told that the particle is in equilibrium. So first, let's try and resolve horizontally. All of the forces to the right should equal all of the forces to the left. So let's just write that expression. 100 cosine 30 plus P cosine theta should equal 140 cosine 45. Okay, it's a good place to start. Let's maybe make the unknown the subject of this equation. P cosine theta, 140 cosine 45, and we'll subtract the 100 cosine 30. Okay, Let's go ahead and resolve vertically. Okay, so the particle's in equilibrium, so it's also vertically in equilibrium. All of the forces up should equal all of the forces down. 100 sine 30 plus 140 sine 45 is going to equal p sine theta. All right, we've already got the p sine theta as the subject. What can we do with cosine and sine? Sine over cosine equals tan. So let's do some division and see if we can produce a tan expression. So tan theta is going to be p sine theta over p cosine theta. Okay, and I'll just speed up this bit. But if we just punch this into our calculators, we'll get tan theta, and we also get theta equals 85.25 degrees. We can substitute that into one of our earlier equations. We'll go for the p cosine theta. To find p, I'll just divide the right-hand side by cosine of the angle we've just found, and that gives us a p-value of 149.5 newtons. So once again, we've used our strategy of resolving vertically and horizontally to find unknown angles and unknown forces. Okay, well, let's look at an example that isn't quite problem solving, but does have multiple steps to it. Okay, so we want to get back to forces and motion. What's different this year is that the force we're going to be looking at isn't necessarily applied in the direction of motion of the particle or the object. In year 12, we had horizontal forces that would move the particle horizontally, or we had vertical forces that would move the particle vertically. As you can see here, we have a diagonal force, but the particle, the object, the box on the ground, is going to move horizontally. So a diagonal force that generates horizontal movement. Okay, as you can see, we always want to make and start with our own diagram. There's lots of additions we'll make to this diagram. Firstly, I'm going to add the reaction force. There will always be a reaction force if there is weight going into a surface. And here I'm going to add the components. So this diagonal force has horizontal component to the right and a vertical component going up. Be sure to label the direction of these forces to be clear what we're doing with them later on. Okay, and I'm just going to annotate in the actual magnitude of these components, 10 sine 30 and 10 cosine 30. So using that quick trick we spoke about before, the opposite will always be a sine function and the adjacent will always be a cosine function. My diagram's complete. I can go ahead and resolve vertically. There are three vertical forces: the reaction force, the hg of the weight, and the vertical component of the force. So the two going up equal the one going down. R plus 10 sine 30 equals 8g. Rearrange to make R the subject, and we'll just punch it into our calculator. And at this point, a quick reminder, our calculator should be in degree mode. For applied, we always work in degrees. Don't worry about radians. So, punch that into the calculator, we get a reaction force of 73.4 newtons. All right, we were also asked in the question to go ahead and find the acceleration. I found the reaction force first. Let's go ahead and find that acceleration. We're going to think about the direction of motion. That's horizontal, and we'll resolve. So the resultant force is going to be F, and then we have our mass and acceleration. Resultant force in the positive direction, 10 cosine 30, and that equals the mass multiplied by the acceleration. The mass we know is 8, and the acceleration is the unknown we're looking for. Some quick rearranging, and we get an acceleration of 5 root 3 over 8. But as a decimal, we'll take that as 1.08 meters per second squared. Resolving vertically, resolving horizontally.